To support our discussions with the world's leading thinkers, please see the video description or visit eism.eu/support. Thank you.
Hello and welcome to A Theory of Everything. Today we're talking for a second time to renowned theoretical neuroscientist Karl Friston. As far as I can tell, today's exchange with Friston is unique among any of his public exchanges. I'm going to take a couple of minutes to explain why. If you prefer to skip this introduction, feel free to jump around as you see fit using the timestamp in the video description. Let me start by saying that today's conversation is the most important and ambitious we've had on the channel to date in terms of understanding the physical foundations of management. Remember that management in the broadest Aristotelian sense includes politics and ethics, which together are the summit and goal of all rational activity. This is deeply significant because all rational activity includes just that, all rational activity. That means that whether you're a theoretical physicist, philosopher, politician, theologian, or anything else, if you can't clearly and scientifically describe from first principles how humans are going to avoid an all-out nuclear war, then you need to acknowledge the limitations of your worldview. This kind of intellectual humility is good, in my opinion, because it leads to better listening. It also puts the human quest for a so-called theory of everything into proper perspective. A theory of everything that doesn't include clarity about avoiding human extinction is not a theory of everything. At best, it's a theory of some things. Today's exchange with Friston is unique precisely because of this, and because of his recent assignment as chief scientist at VRSSSF, a publicly traded artificial intelligence company. The implications of the professor's move into the private sector are far-reaching, in my opinion. Some, but not all of these implications are laid out in a recent white paper put out by Friston and a handful of colleagues. I'll leave a link to the paper in the video description. Among other things, the paper highlights the importance of shared narratives and shared intelligence in the context of humanity's quest for AGI, or artificial general intelligence. This quest for AGI is a proxy for humanity's wish to live forever, which I argue comes to a nexus in social, political, and management theory. Today's exchange with Friston, unlike any of his previous exchanges, represents a first principles approach to put all of the pieces of this complex puzzle together in a coherent way for the general public and for experts alike. Friston's work is important, and what we've been able to accomplish here is far from perfect, but I think it works to get the main ideas across and to further the conversation. Friston has expressed an openness to come back to the podcast, so I hope we can continue to flesh these ideas out more clearly in the weeks and months to come. We also have upcoming conversations scheduled with Fields medalist Michael Friedman, who is leading Microsoft's quantum computing strategy and who recently published or co-published a paper positing a connection between quantum mechanics and political theory. If that strikes you as an odd idea, rewind and pay attention to who I'm talking about. Another noteworthy pending conversation is with Vitaly Vanchurin, the theoretical physicist at the University of Minnesota, who has a series of interesting ideas about understanding the world as a neural network. Other guests in the lineup are Carlo Rovelli, one of the leading theoretical physicists and philosophers behind loop quantum gravity, Bernardo Kastrup, an up-and-coming thinker who says reality is all mental, Donald Hoffman, who is looking beyond space and time for the foundations of reality and consciousness. And Brother Guy Consolmagno, the chief astronomer for the Vatican Observatory. The primary question for all of these men will be the same. What does your work say about how we can avoid destroying ourselves as a species? I hope you'll stay tuned because it's a question that should equally interest all of us. As always, you'll find a timestamp and relevant links in the video description. I've included a link to Professor Friston's complete bio, which is impressive and which I invite you to pause and review if at any point in the coming exchange you start to feel skeptical. Thanks again for your interest, and here at long last is my second exchange with Karl Friston. Professor Friston, welcome back to the channel. I'm really excited to have you back and really grateful for your willingness to continue our initial conversation.
It's a great pleasure to be back.
Well, the first time we met, we talked about free energy, we talked about Markov blankets, we talked about string theory, and we tried to connect, or I tried to connect these ideas to political theory and the existential risks we're currently facing as a species. Unfortunately, we ran out of time before we could get to artificial intelligence, which is a critical piece of the puzzle as far as I'm concerned. So that's what we'll talk about today, and we'll try to put the puzzle together a little bit more coherently this time around. Is that okay?
That'd be great.
Okay, so if it's possible, I'd like to talk about artificial intelligence in three different contexts, which are pretty closely related. First, just a few days ago, you and several colleagues published a paper on how to take a first principles approach to designing intelligent ecosystems. I'd like to start with this paper because as far as I can tell, at least at a very high level, the paper is very much aligned with the concern I expressed during our first exchange about the fact that we live on a planet full of nuclear weapons and conflicting ideas. So this mix of nuclear weapons on the one hand and conflicting ideas on the other is a very real threat. So I'm just going to say it outright. I think this paper that you recently released on Archive represents a really important intellectual breakthrough. So if time permits, I'll explain why I think it's such an important breakthrough. And I prepared a few slides for that if we have time to get to them. So the second thing I'd like to talk about is your recent appointment as chief scientist for VRSSSF. Congratulations on that. VRSSSF is a company that's working on, among other things, artificial general intelligence, and they're doing so based to a significant extent on your research. So that's the second thing I'd like to talk about. And like I said, I think they're very closely related. And a third development I'd like to talk about is a recent paper by Michael Friedman, the Fields medalist, who's at the helm of Microsoft's quantum computing research. He and Microsoft economist Glenn Weil recently published a paper on the connection between quantum mechanics and social systems. So your work on active inference and Bayesian mechanics shares important symmetries with their work. At least that's what I'm going to argue. And given the existential stakes that are on the line, I think it would be interesting to talk about those symmetries between your work and their work. So this is some really cutting edge and interesting stuff as far as I'm concerned. And the implications are extremely profound. So I hope listeners will hang in there with us. So how about if we start with your recent paper on intelligent ecosystems? What a deep and important paper. Can we spend a few minutes on the paper and connect it to your lifelong work on active inference, and then maybe connect that to your position at VRSSSF?
Yes, no, that would be great. You had a beautiful way of summarizing this in our pre-interview chat. So I'm going to call upon you just to paint that picture, which from my point of view, is really a culmination, a convergence of life's work and potentially a quite important and amazing opportunity to make that kind of academic work matter in a larger context, the context that you want to talk about.
Excellent. Well, as far as I'm concerned, first of all, it's just so amazing that just a few days, it was published, or you released it just a few days ago, five days ago or so. And I took a look at it and I was just blown away on several different levels. Maybe the most important for purposes of our discussion now is how it connects, or it's able to capitalize on an entire career, a lifetime of theoretical, highly abstract work, which has important implications, and apply that highly theoretical work now to a really critical aspect of human life, which is the social reality. So it's capitalizing on your lifetime of work, theoretical work in neuroscience and in the physical foundations of neuroscience and active inference, predictive coding, connect that to artificial intelligence now for the benefit of society. I think it's just such an apt way to culminate your brilliant career. And so I congratulate you for that. And I'm really, really excited to witness this. And I'm really happy to be here. So thanks so much for that.
That's very kind of you. And yeah, just to reiterate that point, I mean, this is a very happy convergence, confluence. From a selfish point of view, it is exactly the kind of thing I had in mind as a young man, at the inception of my career, sort of realizing the potential of a first principle account of how we work in a way that actually matters, and meeting a group of people who in a very right-minded way, I think, want to make the next generation of artificial intelligence work for the common good, are all predicated on this notion of shared intelligence, which of course is exactly the focus of the first principle account of self-organization and how we couple to our environment, where that environment, of course, is composed of other things like me, other creatures like me. So it is a very happy convergence.
Excellent. And let's talk about the paper, because there's so many, we could spend at least a couple of days on the various different points that are made in the paper on so many different levels, really from human existential levels down to important ethical considerations and practical, technical implications for how artificial intelligence is rolled out in the future. What to you stands out at this point about the paper and about your assignment, or your assignment at VRSSF? What do you think is the most important aspect of the paper? What excites you the most about the paper? What do you think is the most significant or relevant aspect of the paper? I have my own answers to this question, but I'd like to hear yours.
I'm tempted to hear yours. Okay, well, I'll say what I think, and then you can tell me what you thought I was going to say. Well, first of all, just to acknowledge that this white paper is the product of many months, if not years, of work by people like the head of research and development of VRSSF, people like Maxwell Ramstead, and all his colleagues with whom it's been in discussion with on the VRSSF side. In the past few weeks, really, to coincide with the announcement of my chief scientist appointment, it's been brought to fruition and been, if you like, rendered in a way that is very clearly grounded in a first principle account of self-organization and intelligence. For me, the big thing was being forced to look at what the implication of this understanding of the way that we share beliefs and we interact with others has for the future. So it was a very audacious white paper, rolling out decades into the future. And the basic premise, there were lots of really interesting technical issues about how one will deploy these ideas and this technology, and what is necessary for that deployment practically in terms of what people need to be doing in the next few years, on the one hand. And then on the other hand, there was the ultimate direction of travel, the vision of the future. And for me, the more compelling aspect was, or the most compelling aspect was this focus on a move from the information age to the age of intelligence, and especially the nature in which that intelligence is shared. So it's all about communication. If you were in the neurosciences, this would be a picture, a formal picture of distributed cognition. From my perspective, it's a realization of the fundaments of coupling to the world, exchanging messages in an optimal way that speaks to exactly this notion of how we share beliefs. So the free energy principle and active inference distinguishes itself from most optimization schemes that one might find in, say, artificial intelligence research that are predicated on optimizing some well-defined value function or minimizing some well-defined cost function, and takes us into the world of Bayesian beliefs, probability distributions, very much like quantum physics. It's all about the probabilistic description of the way things are. And in a sense, everything is a kind of measurement or an inference. So technically, it was a move from having information as the currency, or technically finding functions that map from data to some desired outcome, and reformulating that kind of artificial intelligence in terms of active inference and the free energy principle, which brings us into the space of beliefs. It brings us into a different kind of calculus and a different kind of geometry, something that some people cast as a Bayesian mechanics to complement things like quantum mechanics and classical mechanics and statistical mechanics. So that tells you immediately that if you're talking about distributed, a web of intelligence, you're now in the game of talking about the ways in which we share beliefs and communicate beliefs, and that immediately brings you to some very practical issues about the nature of message passing. So, I look at this through the lens of a theoretician on the one hand, but also in making those ideas accessible and providing proof of concept. One also has to put them in silico and write down equations and have software demos of these kinds of this kind of approach. In so doing, you have to commit to how you're going to do this kind of shared intelligence on a computer, how you're going to do it sort of in terms of the computational architecture, and that usually boils down to message passing on graphs. And knowing that if the future is all about sharing our beliefs, resolving our uncertainty, imbuing different things with different kinds of context, confidence, then now that the beliefs have to be passed, the messages have to be passed in a way that communicates probability distributions or beliefs, and then one can appeal to this first principles account of self-organizing systems that have to pass messages from themselves to their niche, to their environment, to the network, to the nodes outside of themselves, and also receive and process and make inference on the basis of messages that they receive. You now know what that mechanics should look like, the mechanics that you would then deploy to specify the nature of that message passing. Furthermore, practically, this tells you a lot about the kind of message passing that is required. I mean, literally, the model language, the form, the structure of the messages, and also the requirements for the message passing protocols. And this brings me to something that I don't know about, but I'm looking forward to learning a lot about, which is the first step. So if you want to realize this kind of shared intelligence, this new age of intelligence on the web, for example, then you're going to have to equip the community, the world, with a sufficient kind of message passing functionality. And that, from the point of view of verses, would be a hyperspatial message language and accompanying transaction protocols. So that's the focus in the first instance of this group of people. It's really paving the way to enable then the deployment of a active inference in the service of realizing our potential. And by our, one could include not just us as the ultimate biomimetic intelligence, but all the intelligent artifacts that that might be out there.
Yeah, that's very interesting. Well, we are actively involved in a number of pretty large-scale European transnational projects. So, and technology normally plays a central role in these projects. So I really look forward to learning more about what VRSSS is doing and maybe incorporate that into one of these projects. So that's really interesting. But you've hit the nail on the head. I think what I was going to say is the most important aspect of the paper, and I've even memorized the sentence that struck me, and it was I think in the introduction or at the end. I don't remember. It says we highlight the importance of shared narratives and shared goals and the emergence of collective behavior. So I think when you speak in this way, obviously technology is an important factor, but you inevitably come up against political ideas and how we make collective decisions. And I think this is something that we spoke about in the our first discussion, that I think your work has important implications for these political and social choice theory questions. So I think this is super, super interesting. Now, this concept of the future, actually, maybe we'll wait on the future for the presentation. As a matter of fact, maybe this would be a good time. Do you mind if I share my screen and we kind of walk listeners through a visual presentation of some of your ideas, and then try to connect them with artificial intelligence, and maybe you can elaborate on in a visual way on not only your work, but what VRSSS is trying to do. And then I'll follow up and try to connect that with the possibilities or the implications of this work for how we come to not only collective behavior, but also collective decisions. Is that okay? That's
great. Before you do that, I just wanted to pick up on that sort of focus you brought to the table, that notion of a shared narrative. I should have said that. That is absolutely fundamental to to this whole approach. And indeed, if you just think about what is language, it presupposes a shared narrative, a common ground. So that's going to, I think, be a really important theme in what you're about to demonstrate, or hold our hand as we walk to unpacking these ideas in terms of multiple agents talking to each other.
Okay, perfect. Then we'll share my screen. Fantastic. I'm glad we agree on that. I think well, the paper is very clear. It's it's upfront about the shared narrative, and it's so important, I think. Okay, I'm seeing myself right in the middle of the screen, so allow me 1 minute to see if I can get rid of that. Try this. Okay, I don't see myself anymore. Perfect. Okay, very good. So through these slides, what I'd like to do is accomplish 4 things. Number 1 is get a visual feel for your work, Professor, on predictive coding and active inference. I think in several of your presentations and in your papers, there's some aspects, of course, are quite abstract and very difficult for non-experts to follow. But some of them, on the other hand, are extremely intuitive, and that's the ones I'd like to concentrate on for the moment. Obviously, your work is very deep and very profound. We can possibly cover it for our general audience in a few minutes, but we're going to try to get the main ideas across. Okay, then another goal, number 2, is to connect that work to conventional artificial intelligence, and then connect that step step 2 to step 3, connect artificial intelligence to physics, and elaborate on your first principles physics approach to not only studying the brain, but studying nature and artificial intelligence. And then lastly, I'll try to say some things about how we can connect AI and physics to political theory. And in this last step is very interesting because, as I mentioned, Michael Friedman and Glenn Weil published a paper recently positing what they call a wormhole between political theory and quantum mechanics. And I think, like I said, I think there's very interesting symmetries taking place here. And if we can stimulate that convergence, I think we're in a much better place to respond to some of the real existential issues and risks we're facing as a species. So on the screen is a clip from one of your presentations before, I think, the Foundational Questions Institute. And I'm going to ask you, Professor, if you would be nice enough to explain this, visual and connect it to your work on non-equilibrium steady state, active inference, etc.
Right, so this is a graphic that tries to give the intuition behind the physics of self-organization. And as soon as you say the word self-organization, you immediately are committed to talking about a self as something, which means that you have to be able to distinguish the thing from everything else. Furthermore, that thing that has the attribute of a self has to have characteristic states that are non-trivial in the sense that they can be measured or observed over a substantial period of time. So technically what we're talking about are dynamical systems that self-organize themselves to restrict themselves to an attracting set of states. And just defining thingness in terms of possessing an attracting set of states, some characteristic states in which you would find me, has some very simple but also very telling consequences for the dynamics of such things that exist in the sense of having these characteristic states. So this is the graphic that I usually use just to try to demystify, but also help people interpret the role of the mathematics that formalizes the dynamics in question. So I ask people to imagine that I'm placing a drop of oil in a cup of water. And what would normally happen in systems that don't have characteristic states is that the ink molecules would diffuse and dissipate throughout the solvent due to random fluctuations at a molecular level. But the kind of systems that we're interested in describing and characterizing are those which have an attracting set, as if for example, in this graphic, the ink molecules gather themselves together, that they were attracted to a particular location in this, say, glass of water. And just knowing that they do this tells you immediately that you can understand two forces that underwrite this aspect of self-organization. The first is the tendency for the ink molecules to dissipate, disperse, dissolve throughout the water. And that, I repeat, is due to the random fluctuations that is exactly balanced by a gradient flow, in the sense that the ink molecules look as if they are diffusing up concentration gradients. So when the diffusion up the concentration gradients exactly counters the dispersive effect of the random fluctuations, then you get this kind of dynamics. You get this, the emergence of this attracting set. So that tells you immediately that there's something fundamentally constructive about the dynamics of things that self-organize, or indeed things that just exist. It looks as if they are always moving up the log of the probability gradients that describe the states that they are characteristically found in. And when you write that down, you basically get the free energy principle, or the Bayesian mechanics that we mentioned previously. Does that make sense?
Excellent. Yes, it makes sense. And I'd like to make another connection that I think will make it even more relevant for listeners. The same mechanics and the mathematics, can it be applied to the disintegration or the integration of a city or a nation or a civilization?
Yeah, yes. I mean, almost by construction, I use the word thing and thingness. So anything that exists in virtue of having some characteristic states has to comply with these dynamics. So it could be a proton, it could be a cell in my brain, it could be my brain, it could be my body, it could be my family, it could be my village, it could be my institution, it could be my society, it could be anything, right up to the level of astronomy and the like. So as soon as you say anything, then you are saying there exists some organization that has some characteristic states of being, and therefore must comply with these kinds, or what we will see in a moment, must comply with these basic mechanics, these fundamental gradient flows.
Okay, very interesting. We'll come back to a question that has come up. In the case of a fundamental particle, such as an electron or a photon, in theory, we don't know if they're made up of anything else. So it would be interesting to talk about what the mathematics is that underlies them. It seems that one potential answer could be the string dynamics of string theory, but we'll come back to that. We'll come back to that because I think it's more important to go to the next slide. Okay, I'm sorry, the video is not working, but can you please explain this this slide?
Right, so this is in effect a computer simulation of the sort of behavior that we've just been talking about. So this is a very early demonstration of self-organization to these attracting sets, to these non-equilibrium steady states that we were talking about. So this, the movie would have been shown here are 128 little molecules, each color-coded, all jiggling around at the bottom of a simulated potential well to provide a mathematical image of a little primordial soup. So the way that this was constructed fairly arbitrarily was just to write down some dynamics of loosely coupled particles that had neighborhood interactions with strong repulsion and a weak electrochemical attraction, where each particle or each molecule was equipped with its own autonomous dynamics. In this instance, it happened to be a Lorentz system, but it could have been anything that showed some kind of stochastic chaos. So it was just to create a little universe. And the idea was, can we find anything that looks a little bit like biotic self-organization or life or structure? Is there anything in this soup that would possess the properties that we would theoretically predict in terms of this self-organizing flow up the log probability gradients of me being in a particular state?
Okay, can you explain the role that attraction and repulsion played in this simulation?
Yeah, so here, the actual details of form, the functional form of these interactions was not very important. You get the same kind of behavior I anticipate we will see in a moment from any kind of simulation under some sort of mild constraints. The role of these repulsions and attractions was simply to introduce a sparse coupling into a dynamical system. So what we're talking about here is the generic universal behavior of sparsely coupled dynamical systems, and in particular random dynamical systems. So we have random fluctuations in the game here. So the equations of motion, which were solved to produce this simulation, have random fluctuations on them to provide a form of stochastic chaos. So I emphasize the sparsity because that's going to be very important in terms of understanding message passing and coupling, certainly at a societal level. It certainly is extremely important in terms of the structure of our world. In this instance, we introduce sparsity implicitly by a certain locality of interactions. So if I have a number of nodes in a graph or molecules in some idealized gas that only see their neighborhood, and if you imagine a big connectivity matrix or a coupling matrix that couples every element of this population to every other member of the population, then that locality forces all the connectivity to be along the leading diagonal. And therefore, you can say it has sparse coupling because most of the allowable or possible connections are non-existent. So very much like many things in our lived world, the local coupling introduces a particular sparsity structure on your causal architecture that has important implications when it comes to carving nature at its joints and individuating certain parts of the system from other parts of the system.
Okay, I asked because, as a parenthesis, Isaac Newton, in the preface to his Principia Mathematica, and I paraphrase here, he says, "I wish I could better understand attraction and repulsion, because I suspect that the whole of nature can be derived from them." So that's just a parenthesis. We'll come back to this later, but I found it interesting that you use that in your simulation, attraction and repulsion. And for the next slide, which is, can you take us from the previous slide, the simulation, to this one?
Yeah, well, it was a lovely quote from Newton there. And of course, we would all acknowledge he was absolutely right. I mean, to carve nature at its joints, if those joints are articulated in terms of the way things couple to each other or connected to each other, everything should be derived from the nature of that coupling. And of course, if everything was attractive, everything would be attracted to a point attractor, which would be not very interesting. And everything was repulsive, there wouldn't be an attractor. So there has to be attraction and repulsion to get these attracting sets. So I haven't seen that quote before, but it's very prescient for.
Yeah, it's impressive. Yeah. At the beginning of the scientific revolution, and not coincidentally, to this day, we still don't really understand gravity, attraction, and dark energy repulsion. I think it's an interesting coincidence.
Yeah, and to the job of linking this to that simulation of a primordial soup. So in fact, this graphic, this image on the screen at the moment, is exactly the same solution, the same simulation as the one depicted in the previous slide. But all that has happened here is that we have color-coded the molecules according to something called a particular partition. So the idea here is to confront and drill down on the quintessential aspect of a thing, a particle, a person, an institution. In this instance, it's going to be a little particle, a virus-like little particle, to drill down on what it means to be something. And the first thing you have to contend with is that you need to be able to individuate that thing from everything else. So that, in a very practical fashion, means you have to be able to identify the boundary, the set of states, in this instance, the molecules, that separate, in some sense, the interior of something from everything else, namely the exterior of something. And it turns out when you look at the the dynamics, and you commit to the notion that the only meaningful separation or individuation has to be that of a probabilistic kind, then we arrive at this notion of a Markov blanket. And a Markov blanket simply says that if I knew all the states of my blanket that enshrouds me, then that is sufficient to predict how I am going to change. My interior, my internal states will change in the sense that I don't need to know everything else in the rest of the universe. So technically what that means is that the internal states, my inside states, are conditionally independent of everything else in the universe if I was given my blanket states. And it's that sort of statistical insulation or shroud or separation that enables me to say that in some way, in some fundamental way, and possibly the only way, I can now separate or individuate me from everything else, where I constitute my internal states and my blanket states. So what we're seeing here is that particular partition, a partition that engenders the notion of a particle comprising its blanket states and its internal states, being realized in this simulation. So what we've done here is color code the internal states in blue, the active states and the sensory states that together constitute the blanket states in red and magenta respectively, and then the rest of the universe, the external states, are in cyan. And if you remember when the movie was running, what we can see inside this sort of synthetic primordial soup is a tiny little creature. Looks like a little bit like a sort of prion or a little virus, with its with a little tail or cilium on the lower left side, wiggling due to the random fluctuations in the self-organization caused by the stochastic chaos, living there quite happily at non-equilibrium steady state, just in virtue of the fact that it can be separated through the statistical independency, conditional independency, because it is equipped with the Markov blanket. So all we're saying here is that this very minimal, very elemental kind of biotic self-organization is a necessary property of any random dynamical system that has a particular partition, namely has a Markov blanket, one of many, many Markov blankets inside it, and each Markov blanket will demark or individuate a particle or a person from everything else.
Okay, very good. So that should have given us a visual, more intuitive feel for Professor Friston's work on active inference, predictive coding, and Markov blankets. Especially, I'd like to draw listeners' attention, especially to the idea of an ink versus oil dropped into water. That dispersion or integration is essentially, it's a nice way to visually intuit how Markov blankets always separate things from their environment, okay? Okay, so this next step, I'd like to connect that work to conventional artificial intelligence. And for this part, I'm going to speak more, and I'm going to ask Professor Friston to correct me if I don't have the work correct in terms of the connections that I'm trying to make here. Okay, so traditional computers are about having inputs that go into a program and have results. So for example, a calculator, you put in the numbers into the program and you get the results. Microsoft Word, you type in your letters, the program gives you the results. The next step in the evolution toward artificial intelligence was to, in addition to the inputs, you assign weights or different parameters into the model, and then you get results. Okay, and then the next step in this evolution from traditional computer programming to artificial intelligence was you have inputs, you assign weights, pass them through a model, you get results, and then you analyze or evaluate the performance. That performance then is used to go back and change the weights or the parameters that you run through the model once again to get the results, and you evaluate the performance. The idea is to get a continuous improvement on your performance by running back through the model continuously. So this is machine learning or artificial intelligence. And this is, in some sense, what is happening with active inference and predictive coding. And the way Professor Friston talks about it is the performance is a precision-weighted prediction error. Professor Friston, would you like to elaborate on this? Is this symmetry a correct way to think about active inference and precision-weighted prediction error?
Yes, I think so. I think the key, well, let's just drill down on the notion of prediction error. I'll beautifully frame this because it connects very, very nicely with that simulated primordial soup that we were just using. So we were illustrating both conceptually and with these numerical simulations, the notion that just to exist as a particle or a person equipped with a Markov blanket means that you, all of your dynamics, everything that comprises you, namely your blanket states and your interior or internal states, has to, very much like the ink molecules, perform a gradient descent on the log probability of being in your characteristic states. That is a really simple but quite fundamental observation, because you can read the log probability of being in a characteristic state through the lens of either a statistician or somebody machine learning or information theory. So this quantity has many different names. So the log of the probability of an event or being in a particular state, for example, if I take the negative of that, then that's self-information, which basically means that all my dynamics, all my flows, if I possess this attracting set, can be read as minimizing the average of self-information, which is entropy, which immediately tells you that the things that exist will have to counter the natural entropic forces that embodied in things like the second law that would cause the dissipation of my states of being. So that's how somebody in information theory or thermodynamics might interpret it. But you can also interpret it in terms of a statistician. So that log probability of me being in a particular state, given I am me, can also be read as the marginal likelihood of me being in that state, given me as a model. So that can also be read as Bayesian model evidence. So what this gradient flow, this fundamental dynamics that accompanies existence, looks as if it is the dynamics that you would see if you were trying to maximize the log model evidence or the log marginal likelihood. And now we're getting to a view that people in machine learning would be quite comfortable with. So for example, if I now replace that model evidence or log model evidence or log marginal likelihood with a variational bound, we don't need to go into the technical details of that, but just to say that practically the way that you evaluate these things is to replace it with an elbow, an evidence lower bound, or a free energy, a variational free energy. And what we can say is to exist is just to have a dynamics that looks as if it is climbing the gradients of a negative free energy or a positive evidence lower bound elbow, and that's the F on in the first equality on the upper right. Excuse me. It transpires that under some simplifying assumptions about the nature of random fluctuations, the gradients of the free energy can always be written down as a prediction error. So that symmetry you were talking about there, I think hits you in the face when you realize that the fundamental dynamics of existence, these existential dynamics, can be read as a gradient flow on prediction error, where you're trying to minimize this self-information or free energy that always can be interpreted as a prediction error. That now allows you to think about the optimal performance, namely just existing, maximizing my marginal likelihood on the evidence for my models, sometimes articulated in machine learning as explicitly a particular kind of cost function. I'm thinking here of variational autoencoders, for example. So variational autoencoders have exactly this variational free energy as their performance metric. So now what we're doing is we're reading this sort of universal dynamics of existence as if it was trying to optimize some performance measure, which just is this free energy or evidence bound. That is exactly a minimization of prediction error under some simplifying assumptions. And in the moment, I imagine you're going to ask or take the viewers through the simplicity of what a prediction error is. It really is very simple and beautifully so. But just to sort of finish off what we're talking about here, the second equality is just unpacking this fundamental flow here articulated in terms of the Helmholtz decomposition of this gradient descent on free energy in terms of what people might recognize as a Kalman filter or Bayesian filter, also using linear quadratic control, where all we have is a prediction of my expectations about the causes of my inputs, plus an update, which is going to be in proportion to the mismatch between what I thought was going to happen and what I actually observed. So the difference between the predictions of my inputs and those inputs, crucially weighted by the precision I afford those prediction errors. So if I think these prediction errors hold a lot of very precise information, I'm going to assign them much more weight, and they're going to have much greater influence on effectively my belief updating, as opposed to if they're very imprecise, very noisy, very low SNR prediction errors, in which case they're not going to have much weight in relation to my predictions, my prior beliefs about the next state of the world at the next point in time. And I've slipped in here the word belief, if you noticed.
Yes.
So the slight that symmetry, I think, I repeat, is beautifully rendered by these graphics, but there is a particular move which distinguishes conventional machine learning and artificial intelligence to the red background active inference, and that's the performance is always measured in terms of the quality of your belief updating. So it's a quintessentially belief-based view of optimization that has to be written down. It has to be a calculus of probability distributions and Bayesian beliefs, which means that these flows have to be described as flows on a statistical manifold in an information geometry that is defined by these probabilistic beliefs, by these probability distributions. And just for your interest, the ones that inherit from the notion of the Markov blanket are specifically the beliefs about the outside external states of affairs in the world that are encoded by the internal states. So for every internal state, there is a corresponding belief about the outside, and I have to actually, to perform, to get that optimal performance that you nicely described earlier on, then I have to change my beliefs in a particular way, and that particular way just is to maximize the evidence for my implicit model of what's going on the outside.
Okay,
I
fantastic.
I was just about to apologize for giving you too much detail there, but
No, that's great. That's great. I think listeners will appreciate it. I'd like to emphasize the information, the dual aspect information geometry, which I think is one of the important takeaways from this. And I think we're going to see this now in, well, this is a lot of what you've talked about previously, no? Sensations, prediction error. Yeah.
Absolutely. I think this, I like this slide because, we've been talking about information geometries, variational bounds, Helmholtz decompositions of the sort that, a physicist, a classical physicist would be quite comfortable with. They probably double Dutch to everybody else. But if you remember that the things that matter from all of that physics of self-organization, and sometimes I like to refer to it as a physics of sentience. All that you need to take from it is that the things that drive your dynamics are these gradients of a variation-free energy that just are prediction errors. All you need to remember is you can describe everything in terms of minimizing prediction error. So what would that look like from the point of view of a person? Well, all that we're saying is that if prediction errors are just the difference between the data that we sample and garner actively from the world and those predictions that are generated by an implicit model or that is entailed by our internal states, then we can think of the brain minimizing prediction error in one of two ways. There's only two ways you can minimize that difference, and that's either by changing your predictions, and that would literally be changing my mind through my internal dynamics, my neural activity, the kind of thing that we measure when we do brain scanning or EEG analyses, to make my predictions more like the sensations. Or, and this is the key twist, the inactive turn, you can make the sensations more like your predictions if and only if you can change the world. You can act upon the world to selectively sample different sets of, or take another perspective on the world that's generating your sensations. So what this basically says is that you can understand this fundamental existential physics of sentience very, very simply in terms of any artifact, human or otherwise, perceiving the world by changing its mind, by changing its implicit beliefs in order to make the predictions more like the sensations, basically perceiving, or acting upon the world to make the sensations more like what was being predicted. So basically action now becomes the gathering of smart data, and the smart data is just the data you predicted under your beliefs about a nice world.
Excellent. Now, this slide here gets us closer to your dual aspect information geometry. Can you elaborate on this?
Yes, I can. You're looking a bit hesitant because I could spend too much time talking about it, so please stop me if I over answer. So this graphic accompanies this sort of physicist perspective and is effectively making the point that at non-equilibrium steady state, or when the thing in question, the particle or the person or institution in question occupies one of their characteristic states, there has to be a generalized synchrony between the inside and the outside. And I suspect you're going to want to talk about this notion of generalized synchrony when we start to talk about sort of population dynamics in politics and the spread of ideas and the like.
Sure, but it is not only that. I think that generalized synchronicity also is interesting in terms of the holography and the holographic principle.
Absolutely.
Which if I remember right, you or some of your colleagues are working on the holographic implications of this work, or maybe I'm.
No, that's spot on. Absolutely, yeah. So that sort of quantum information theoretic take would treat the Markov blanket as a holographic screen where the inside and the outside are reading and writing to the same screen. And what you've just hinted at is basically the principle of unitarity, entailing an ultimate entanglement between the inside and the outside. From a classical perspective, that would look exactly like this generalized synchrony we're talking about. To put that very simply, what this graphic was meant to portray was, if it's the case that there is this sort of vicarious two-way traffic across the Markov blanket, or two-way reading and writing to a shared holographic screen shared by the environment and the thing in question, then it has to be the case that for any state of the Markov blanket, or any, if you like, state of the what is written onto the holographic screen, there has to be a most likely internal state and a most likely external state conditioned upon that Markov blanket. Because by construction, if you remember, the definition of the Markov blanket is that there's conditional independence between the inside and the outside given the blanket. So to put that another way, for any given blanket state, there is a unique distribution on the internal states and a unique distribution on the external states, which means that now there is a mapping between the most likely values of the two. So now that you've induced a synchronization manifold, there's a unique and under some simplifying assumptions, a diffeomorphic mapping between the inside and the outside that just is a statement of generalized synchrony. More interestingly, in relation to your particular question, what that means is there is also a mapping between a point in the state space of the interior, the internal state space, namely the expected value, the most likely value of this probability distribution for any given blanket state, and the actual probability density over external states. What that means is that you have induced effectively what's called a statistical manifold, which means that for any given internal state, I can imagine it wandering around on the synchronization or statistical manifold, and each point corresponds to a probability distribution over the outside. In other words, a belief about states of affairs that are hidden behind my Markov blanket or behind the holographic screen. And that's quite remarkable, because what that means is there are two kinds of information geometry that describe this kind of statistical manifold. Because not only does any one point on the statistical manifold describe a probability distribution or a belief about the outside, there is also a probability that I will be at that point, given I am the kind of thing I am. So now you've got, if you like, two kinds of information geometry living on the same statistical manifold. One is the belief about states of affairs out there that are forever hidden behind my screen or my blanket, but also there are a probabilistic thermodynamic description of my brain state or of my internal state. So now you've got a nice picture where you've got this dual aspect monism, in the sense that there is a, if you like, probabilistic statistical description of my internal states that can either be read as in terms of beliefs about the outside, so beliefs about something, or it can be read as a thermodynamicist might read it, as a description of how likely am I to be in this state. And that thermodynamic aspect is the intrinsic, appeals to the intrinsic geometry, and has very practical and real implications. So for example, any movement on this statistical manifold, in other words, any change in my brain state, has, on the one hand, an extrinsic aspect. It can be read as belief updating, but from the point of view of me looking at a brain in action through, say, the lens of brain imaging or with an imaging device, there is also a movement in the likelihood of that particular configuration of the brain. And we all know via Landau's principle and the like that costs energy. You can't change the probabilistic state in the system without destroying information, and that costs energy, which means that as I change my mind from the perspective of the Bayesian mechanics, I also have to expend energy by moving on this manifold, and we can measure that. And that's exactly what we measure when we do things like functional magnetic resonance imaging, literally measuring the increase in the energy consumption as supplied by blood flow to particular parts of the brain when they're updating their beliefs more vigorously.
Very interesting. Well, that's one point that I'd like to make very quickly, is that a fascinating aspect of your work is that you have actually come to this through your work in neuroscience, which is really fascinating. Okay, so this is a summary of what we've talked about so far. We won't spend too much time on this. Simply drawing the reader's attention to the fact that a brain has sensory states and active states, external states, and the internal brain states. There is some symmetry or synchronicity between those two, or there's a movement or a pressure for there to be some synchronicity between these two states. And that is an important aspect of this dual aspect information geometry. Would that be a correct way to describe what we're seeing here, Professor?
Absolutely, and a very succinct description, which I'm just going to embellish by noting that the blanket states that are constituted by the sensory and active states only are blanket states in virtue of the sparse coupling, and in particular the unidirectional coupling between sensory and internal, and between active and external states. So this is where the sparse coupling really starts to bite in terms of defining these, this Markov blanket and the ensuing symmetry. And that symmetry is so important, because anything you believe about the brain, you have to believe about the environment. So mathematically, there is an absolute symmetry here.
Okay, fantastic. Very good. So we've covered very quickly the first 2 points. Now we're going to try to connect AI to physics. Okay, that's our third point. And then we're going to close with our final fourth point, which connect AI and physics to political theory. Okay, so this graph is interesting because through this graph, you connect the Fokker-Planck equation to Feynman's path integral formulation, and of course, the very famous Lagrangian mechanics, to the future. Can you explain this?
Right. Yeah. So this has got some of my favorite equations on, but I'm not sure they're going to be your viewers' favorite equations. So I won't go into the details, but just to try to summarize the architecture of this graphic that is using these equations almost iconographically, just to sort of a nod to where all the physics come from. So on the one hand, we have one version of physics, and in fact, one could actually argue all of physics, if one puts in special constraints on random fluctuations to, or makes ensemble exchangeability criteria, one can derive all of physics from the Langevin dynamics and the equivalent Fokker-Planck description, just noting that the Langevin dynamics just describes the trajectory of a particular state, some abstract state. The Fokker-Planck pertains to the probability distributions over those states, and then the path integral formulation would be an equivalent formulation that specifically deals with probability distributions over paths, over the trajectories from now into the future, and indeed the past. So all of that is off-the-shelf, vanilla, and very beautiful physics, and summarized in terms of principles that one could apply to understand or describe physics, such as variational principles of least action, such as things like James's maximum entry, constrained maximum entry principle, certain sort of gauge theoretic principles, all different takes on I think, exactly the same thing, which is what falls out of this kind of treatment. So I've here focused on the principle of least action, and in particular sort of variational action, as a description of the way things are when they are in this non-equilibrium steady state. And an example of that would be, say, the Schrödinger time-independent wave equation would be one version of this kind of maths. So the game here then is to say, okay, that's how we have a physics of things, very small things at the quantum level through to very, very big things, as described by Lagrangian mechanics, all unified and all summarized in terms of a variational principle of least action. What would happen if we just simply took our state space X and applied the particular partition? So now we're talking about the states of something in relation to everything else, here formalized in terms of this free energy functional, which is effectively a description of the probability distribution of beliefs about the outside given the inside. So nothing has changed other than the fact we've now put a Markov blanket into the mix, into the game, and then just rederive everything. And that's basically what you're seeing on the right-hand side. So what that tells you basically is effectively that active inference just is a principle, or the principle, or a variational principle of least action that applies when you have a particular partition that individuates something from everything else. What is the action? It's just the path integral of the free energy, the variational free energy. And if you remember, loosely speaking, we can think of the variational free energy as prediction error or surprise. So all we're saying is that things that exist that can be individuated in virtue of having a Markov blanket simply are going to be described very simply as pursuing the paths of least resistance and least action that minimizes the expected or average surprise. What is that? Uncertainty. We're just saying that anything exists can be described as if it is behaving as if it's trying to minimize its uncertainty. And I think that's going to be a useful thing to remember when we start to talk about coupling between two things who are both trying to minimize their uncertainty about each other, because then we start to get into the interesting game of what this kind of mechanics, this physics of sentience, read simply as making sense of the sensory states in the service of collecting the right kinds of active states, how that works when we start to have an ensemble of sentient agents all exchanging among each other, or if you like, sharing a holographic screen, the same Markov blanket.
What is the relationship of active inference to time or to the future?
Right, so this view of describing things in terms of a pathological formulation and a minimization of the free energy that I would expect in the future has some really interesting interpretations. Anthropomorphically speaking, what we're talking about now is the behavior of a certain class or kind of particle that effectively can predict the future, and in particular the consequences of its own action. So when one drills down into the functional form of the path integral in the space of active inference and in the space of the Bayesian mechanics, what you can see on this slide here is a particular reading of the constituents of the free energy. So from the physicist's point of view, indeed from the point of view of E.T. James, the free energy in question is really the entropy of my beliefs about what's going on outside. And you'll notice here it's denoted by Q subscript alpha, open brackets, external states, eta at a particular time, we don't need to worry about that, but the key point is it's the entropy of my beliefs about what's going on the outside, and an energy term which can be read effectively as the an accuracy plus a constraint afforded by prior beliefs that are embodied or entailed by the structure of my brain in this instance. So you can, the expected free energy or the free energy path interval that I would expect pursuing a particular course of action can be decomposed into this energy and entropy. But you can also read these things in terms of how a statistician would understand it, which actually, and the statistician would actually split things into risk and into accuracy and complexity. And then you ask, well, what does the accuracy and complexity look like? How can it be interpreted when we roll out into the future by taking the path interval from t equals 0 to some horizon in the future? And interestingly, what it looks like is that the risk, the complexity, the expected complexity term now becomes something that an economist would recognize as risk. It's basically scores the difference between what I a priori expect will happen relative to what I actually anticipate will happen if I do this, if I act in this particular way, or if my active states follow this particular trajectory. So the risk now scores the degree of surprise or departure from what a priori I expect to happen, the states I prefer to be in, because those are my characteristic states. And then the accuracy term, or more precisely the inaccuracy term, now looks like something that we call ambiguity. It's basically the uncertainty inherent about internal states given my sensory samples. So the classic example here would be the first thing I do when I go into a dark room is turn on the light, therefore affording my visual sensory input a kind of precision which resolves the resolves the ambiguity. So crucially, what we've started to do here is put a semantics on what is effectively just a Feynman path integral formulation, but unpacked in the context of a particular partition, but a semantics that actually has which is heavily anthropomorphized. So what we're saying is that things that exist can always be described as minimizing their risk in relation to some preferred states of being. Or they're also, what we're trying to do is to sample the world to minimize ambiguity, namely to try and resolve uncertainty, which brings us back to the expected surprise, which is just the average or the path integral of our variational free energy. So to cut a long story short, what that means is there is always a description of the behavior of things that manage to individuate themselves from their environment, which means that they will always look as if they're trying to resolve uncertainty about the states of their eco-niche or their environment or their heat bath in which they are embedded. So that sort of resolution of uncertainty is absolutely central to active inference. It unpacks in many different ways. Another way of rearranging these equations is to note that the expected free energy can be also decomposed into a linear mixture of two terms that you find in Bayes optimality. The first one is expected information gain, of the kind articulated by Dennis Lindley in the 1950s as the best way to design an experiment to get the most uncertainty resolving information, maximizing your information gain. Recast as active learning by people like David McKay in the 1990s, and now active learning be an important part of artificial intelligence and machine learning. That's the epistemic part, that's the expected information gain part. But there's another part, which is the expected value that inherits from Bayes indecision theory. So if I interpret my log probability of preferred states or characteristic states that just is a specification of this attracting set that drives this gradient flow that we were talking about as a value, potential, a log probability, a potential function, a value function, the negative being the self-information would be the cost function. If I interpret that log probability as a value function, then I have, as part of this surprise minimizing imperative encoded by or expressed by the expected free energy, I now have exactly expected utility of the kind you'd find in economics. So what that means is you've now got a physics that basically says anything that exists will look as if it's trying to maximize its information gain under constraints. What are those constraints? Well, I don't want to wander into states that I would find very uncharacteristic of me, that I find aversive, that have a high cost in the sense of Bayesian decision theory. So that's a long-winded, but I think useful perspective on how you link this physics of thingness to the sorts of behaviors which we understand as optimal when it comes to planning, decision-making, or more generally, selecting the most likely course of action into the future.
I'm reminded of a respectful challenge that your colleague, Michael Levin, issues to people who don't like to talk about planning and goals in science because they're teleophobic. And so Michael Levin says, listen, this is the language that we use, and it leads to actual experimental progress. If you have a different language or a different model that you think would be better, show me the model. For now, I'm regenerating animal limbs using this language and this conceptual framework, and it's working for me. So until something better comes along, I'm going to stick to this way of thinking and working and conceptualizing. So I think it's very, very, very interesting. Just to remind readers that we're dealing with very abstract conceptual things here, but there's actually very practical, empirical work being done along these lines by some very interesting researchers in every corner of the world. Okay, so I think the reason I asked about the future, and even if we anthropomorphize, is that the conventional way of thinking about quantum mechanics and the so-called collapse of the wave function is that causes come from the past. Only the past is relevant to how physics or physical systems evolve. But there's an alternative approach spearheaded by Yakira Harnov, among others, where they posit that the future has an impact on the evolution of a system. So there's not only one wave function traveling from the past to collapsing in the present, but rather what we experience in the present is a combination of a wave function that evolves from the future to the present and from the past to the present. And this seems relevant, especially because the formalism is quite advanced and quite relevant to, I think, what everything you're trying to accomplish. I say this as a parenthesis because, among other things, we haven't talked about how active inference solves, for example, the measurement problem, or how active inference fits into the so-called quest for a theory of everything. And I think this is an important piece of the puzzle. We're running short on time. I'd like to just leave this here as a point of reflection, and we'll come back to it as necessary. Listeners to the channel will be familiar with this two-state vector formalism, but perhaps it's new to you. I don't know if you're familiar with it, but I think it's the formalism, the mathematical formalism, and the conceptualization, I think is actually very relevant for active inference. Okay, so the next point I'd like to make here in our goal to, to connect artificial intelligence to physics is this concept, this dual aspect information geometry actually maps nicely to something central to 500 years of advance in physics and in science. Has arrived to the string theory, which is our best in terms of number of adherents, impact on other areas of physics and math, our best approach to reconciling quantum mechanics with general relativity through string theory. And an essential part of string theory, or one of the most successful aspects of string theory, which is still a theory in progress, is the so-called ADS-CFT correspondence. And this ADS-CFT correspondence, also known as the holographic principle, posits that there is a symmetry, an information geometric symmetry between the boundary of a space and the interior of that space, which is a lot of what we've been talking about today with Professor Friston. So there's an interesting connection there. At this point, a conceptual connection, but I argue, and am working on the actual mathematical tools that come from string theory to add robustness and power to a lot of the arguments being set forth here. And speaking of symmetry, what we see on the screen here is a certain symmetry posited between how information is processed in animal brains through Markov blankets and how information is posited to be structured in a so-called DS universe. Again, more on this at another time, but what I would like to draw the reader's attention to is that aspect of symmetry and dual aspect information geometry. And so now what we see on the screen is at the very core foundation of string theory. What we see on the screen now is the Hamiltonian of an open-ended relativistic string. And the Hamiltonian and the Lagrangian, of course, is connected. And what I'd like to draw the reader's attention to is how the Hamiltonian, the energy, evolves as mass squared. So this will be an important point for our last part of what we want to do here, is connect everything we've talked about today so far, a lot of Professor Friston's work, AI and physics, and now connected to how we can use these principles and these ideas and the mathematical formalism to make important progress in how we organize ourselves as societies, as nations, as a human species. So if that's okay, Professor, we'll spend the last part of this talk on how we can connect active inference, artificial intelligence, to some interesting developments in political theory and in a branch of economics known as social choice theory. In social choice theory, it studies formally, mathematically, rigorously, how we can make decisions from those shared narratives, right? Because as people, we have narratives about the nature, our nature as individuals, the nature of our environments in which we live, our families, our companies, our cities, our nations, and how we reconcile those narratives into a collective decisions, into politics, is studied in social choice theory. But as Professor Friston has made clear here, or in his paper rather, in the recent paper, a lot of the challenge is how do we apply these shared stories using the professor's advances in active inference, Bayesian modeling, etc. So back to this graph about inputs and weights being passed through a model to get results. We can say that, or compare this to the inputs and votes that go into a policy at the community level or at the national level. to get results, right? This is social choice theory or political theory. So people go into a vote on policy. How many votes does each person get, right? If we have a democracy, for example, one person, one vote, we see the results, right? Everybody votes on a certain policy. The policy is enacted. We notice the results. Okay, if we apply the same principle of machine learning, artificial intelligence, okay, those results go back in to the original model, and we might ask, okay, the results are not optimal. So how can we improve those results? Can we give 1 to 10? Let's test the results. If we give 1 to 10, in other words, change the voting parameters. Go back, test it again, reverse it. Let's test 10 to 1. Okay, so if our goal is long-term survival, then a lot of the mathematics and the formalism and the advances that we're making in artificial intelligence, the idea is that we can apply that to social choice theory and to political theory. So the question is, what are the right parameters, right? And I would argue very quickly that if everything we've talked about today is right, and there is an actual physics at work here, that physics at the most fundamental level, the Hamiltonian or the Lagrangian, evolves as mass squared. And this, I think, is going to be a promising piece of mathematics to incorporate into a lot of what Professor Friston is working on now, and a lot of what the company VRSSSF is trying to accomplish at a social and enterprise level as well. So I think with that, I've abused your time today, Professor Friston. You've been extremely generous again. I think we've left listeners with a lot of information to reflect on. I'm glad it's been recorded so that people can review it and ask questions. Professor Friston, what are some next steps? What are some next steps for you? Can you fill us in on that?
Yes, I can. Before I do that, and I'm mindful that I'm going to have to come back, aren't I? I can see we're going to have to finish this conversation.
Fantastic. Yeah, no, you're always welcome. You're always welcome. It's very deep. It's very deep, and there's so many things that I mean, I was listening to you, and my mind was just going off on so many different tangents, because almost every one of your sentences has a lot of profundity to it and a lot of implications. So it's difficult to grasp. It's very abstract. Go ahead.
Yeah, I was just thinking your last summary was the same for me. I mean, I just wanted to pick up, perhaps it's a theme we could develop in a few months' time, but that last treatment about sort of voting, social choice theory, population dynamics of voting, spread of ideas, and that kind of thing. You were framing in terms of what is the agenda, and you used a phrase which I thought was quite prescient and I think important, where you were likening the ultimate agenda was a kind of equilibrium. And I would imagine part of that would be a synchronicity and a synchronization and a harmony.
Exactly. Yes.
I think that's so important. And just as a layman now, it seems that re-specification of the direction of travel of what is a good thing to do is very important. It is not growth, it is sustainability. The aspiration is not to move away or to have the slope goes up, but to keep things at equilibrium. So some other ways of articulating that, it is equilibrium, which is of course one expression of the dangers of inequality, for example, extremists.
Sure. And polarization, polarization. You can't have, infinite polarization. It won't work. It won't work at the cosmological level, and it certainly won't work at the human social level.
So I think that's something we should talk about. And my point being, of course, that, as a physicist, this all starts with how on earth can I describe a system that aspires to a non-equilibrium steady state? So it is that steady state aspect which is at the heart of all of this physics that we've been talking about. And it's nice that your ultimate agenda highlights and identifies exactly the same phenomena. That notion of sustainability over time is the real agenda. So I wanted to say that. In answer to your question, what are we doing next? Yeah, lots of things. In fact, practically, I have a meeting tomorrow just to explain with my colleagues at Versus R&D or to discuss what to do next. I don't think I can answer that fairly, but I do think that now the transcription of the first principle account afforded by active inference into an ensemble of intelligent agents, be they people or artifacts, who are all doing the message passing and doing that communication and doing implicitly their voting and belief sharing. That's both theoretically and practically the next big thing to crack. There are so many unanswered issues from the point of view of putting together lots of intelligent inferring systems, Markov blankets of Markov blankets, and particularly the sampling of data. Another key theme that you were figuring at when you were manipulating the number of votes per person. I was reading that's basically the precision, how much weight do you ascribe to these votes? That's going to be a really crucial thing. Who do I listen to? And of course, it has implications in terms of being able to detect fake news, for example. So all of these are really important aspects of the mechanics that you would associate or would need to understand to formalize distributed cognition or shared intelligence. So that I think, I'm not saying that's what I'm going to do next, but that's certainly what I would like to do. And those are the areas that I think present the immediate challenges.
Well, fantastic. I'm glad we see eye to eye. I think you're right. This is so fundamentally important. Well, I think at the very least, what I've been able to do today is to celebrate your transition from academia and theoretical work to a new phase in your mission and vision, more practical phase. I think a really important phase, especially because of where we are now, the juncture we're at as a species. I think is important. I think it makes me a lot more optimistic.
Wonderful, and thank you for your very kind words about my colleagues at Versus. They'll be very pleased to hear you say that. I shall tell them on return. Thank you.
Fantastic.
To support our discussions with the world's leading thinkers, please see the video description or visit eism.eu/support. Thank you.